This is the task that DITTO approached. We propose a new implicit 3D surface reconstruction method. This task involves reconstructing 3D meshes from a given sparse and noisy point cloud. On this page, we will explain the goal of our project. Our proposed method, DITTO, has attained a new state-of-the-art in implicit 3D surface reconstruction. We present the reconstructed result at both object and scene levels. As you can see in the figure, our approach can precisely reconstruct the 3D structures, particularly challenging elements like thin and sharp components. This improvement in performance is attributed to our network architecture, which is utilizing multiple latent types, including grid and point latents. On this page, we compare the concept of DITTO with baseline method. Baseline approaches have typically focused on the type of latent to represent 3D geometrical information. In convolutional occupancy network, grid latent such as voxel and triplane is employed to store 3D geometry. The strength of grid latent lies in its stability derived from its regular grid structure. However, grid latent struggles to preserve details due to the resolution constraints and quantization. On the other hand, POCO explicitly utilizes point latent. Point latent can preserve more details than grid, but its unstructured data type occurs ambiguity. Our approach aims to utilize synergy between grid and point latents. ITto already has explored a similar idea. However, we discovered that ITto is somewhat biased to grid latent, and its utilization of point latent is limited, and its decoder only uses grid latent. Therefore, we emphasize the point latent to maximize the synergy between grid and point latent. This is the overview of our approach. DITTO comprises both encoder and decoder architecture. Our dual latent encoder takes a point cloud as input and produces refined point and grid latents. Within the dual latent encoder, a point encoder extracts shallow point features and projects them into a grid latent space, such as voxels or triplanes. These point and grid latents are further refined using a UNet constructed by our proposed DLL modules. In our integrated implicit decoder, occupancy of given qualifications are estimated based on the provided refined point and grid latents. Further details will be explained in the next slide. On this page, we will explain the details of our proposed DLL module and compare it to the ITto baseline method module. The ITto module refines both given grid and point latent. The grid latent is updated using convolutional network and then projected into the point latent space. Both given and projected point latents are updated using linear layers and subsequently fused together. The fused point latent is then projected back into the grid latent space. However, the ITto module does not fully utilize the point latent, as it is only updated using linear layers, making it difficult to leverage the embedded 3D geometric information between points. To address this issue, our DLL employs a DSPT layers to further refine the point latent. In addition, we introduce an extra residual connection to enhance fusion of both original and projected grid latents. This section provides details about the DSPT module. DSPT functions as a window-based transformer, similar to swing transformer, DSVT, and flatformer. In a DSPT module, the point cloud is sorted based on the coordinate of a specific axis. The point cloud is then divided into point windows, each containing an equal number of points. Within each window, positional encoding and self-attention are applied. After processing, the updated point features are restored to their original order. In a DLL module, the DSPT process is applied 3 times with the X, Y, and Z axes, respectively. On this page, We will explain the integrated implicit decoder called IID. IID extracts query feature, which is the red star, by interpolating adjacent grid features at query location. We find the nearest point using KNN from query location and extract point and grid features of each point location. Then we concatenate the grid endpoint latents into integrated neighbor features. After that, we apply self-attention between the query feature and integrated neighbor features to estimate the occupancy value. There are two reasons why IID works better than decoder of ITto. First, ITto uses grid latent only, but we can utilize further detailed features from both grid and point latents. Second, IID can utilize adaptive region of interest. For example, when the query point is near the surface, we need narrow ROI to capture frequently changing occupancy value. On the other hand, when the query is far away from the surface, wide ROI is better to capture global information. IID can have adaptively choose the ROI size by utilizing nearest points, but ITto has a fixed ROI. We will introduce more details of our integrated implicit decoder. We already explained how to acquire query feature G0 and neighbor integrated features from G1 to Gk in the previous slide. To update the query feature, we apply self-attention layers for a sequence combined of the query feature along with the neighbor integrated features. As a result, we can get occupancy value by applying linear layer to the updated query feature. This is the object level comparison result with previous methods. As shown in the table, we achieve significant improvement over previous methods across all metrics, regardless of point sparsity. As highlighted in the yellow boxes, the reconstructed measures of our method were being restored not only the overall structure, but also the challenging sharp and thin structures. These results show that our DITTO model has higher capability to preserve details with greater stability. These are the thin level comparison results with previous method. As shown in the table, we have also achieved significant improvements over previous methods across most metrics. As highlighted in the red, yellow, and blue boxes, we successfully reconstructed challenging cases, such as lamp and the detailed features of chairs. Interestingly, previous methods using grid latent often struggle with thin-level reconstruction when they employ tri-plane latent, so they typically use voxel grid as a grid latent. However, voxel grid requires cubic memory and computation, leading to slower inference speed. On the other hand, our DITTO model achieves better reconstruction performance with tri-plane latent than voxels. We think this is possible because the point latent successfully compensates for the weakness of tri-plane representation, which is more abstract than the voxel grid. These are the reconstruction results for the unseen dataset. We trained our models on the syntactic rooms dataset and then applied them to the scannet dataset. Despite the dataset being unseen, our DITTO model can more successfully reconstruct the overall shapes and details of the given point cloud. These results demonstrate the robustness and generalization capability of our DITTO model, as it can accurately reconstruct complex shape and fine details, even when applied to new unseen dataset.